So thank you, Zhiqiang, and thank you for Professor Wu for the invitation. It's a great pleasure to present my research here. And the topic is about using deep learning model to unlock insights from ECG data. We know that cardiovascular disease is a leading cause of mortality globally. In the UK, there are 7.6 million people live with cardiovascular disease. And for example, there are 1.6 million atrial fibrillation people in the UK, and also 2.3 million coronary heart disease. So people are living with this condition. And in particular, those cardiovascular disease often linked with other health conditions, for example, stroke and also hypertension. So those complications together impose a significant healthcare strain on our NHS system. And we know that ECG is a widely used screening tool for CVD diagnosis. So ECG is normally it's quick, non-invasive, and also cost-effective. So this plot shows a standard 12 disease test. So normally for each ECG lead, they last for 10-second duration. And by examining the morphology features in the ECG test, we can use it for heart condition diagnosis. For example, identify arrhythmias, heart attacks, and also other conditions. And also for health risk prediction. For example, we can use it for in the ICU condition, and also we can use it for wearable monitoring. Um, so actually, there are many applications of AI-ECG in literature. So this figure shows a general pipeline of ECG analysis. For example, we can use a ECG test. For example, this can be either this standard ECG test, or we can use it from wearable devices. So with this input into this, so first we do data filtering, normalization. So this is signal pre-processing. And then we have this ECG input passes through different blocks of this deep learning model, and then it can automatically learn latent features from the ECG data, and then can output for the diagnosis and also risk prediction. And the AI ECG has been used for atrial fibrillation detection, screening OMI, and also mortality risk prediction. And in recent publications, they use AI ECG to detect structural heart disease. You can see there are many applications, but actually it's quite challenging for ECG interpretation using this deep learning model. We know that there are rich information of morphology features in the ECG. For example, by examining the QRS complex, we can make it for diagnosis of different types of arrhythmias. But then if we use AI ECG, so for this deep learning model, this is an automatic process. It learns from the raw ECG, and then for the output for diagnosis, it would be very difficult for us to explain what sort of features, morphology features that have been used for diagnosis. So that's something like what we say black box style for this kind of diagnosis. So that's would be difficult for clinicians to understand for mechanism for the diagnosis. Generally, there are two ways of ECG interpretation in current research. So for example, for this research, they use random forest model combine the sharp value for this interpretation. They first calculate the morphology features manually. And for example, they do segmentation, calculate the QRS complex, and calculate other morphology features and the input into this random forest model, and then calculate the importance of the sharp value score. And then it can be used for the risk prediction using this model. But generally, when we use for this manual calculation, they may introduce some additional artifacts for the calculation, and also for the random forest model, it has a limited capacity to explore the dynamics and also the interconnection between different morphology features. So this is the first type using sharp value for the interpretation. And in the second way, we use GradCam module for the interpretation. So you can say for this research, they treat this ECG as an image, and with the image input into deep learning model and learn these important features for the prediction. So in this figure, you can say they highlight this pink part would be important information, but actually it's quite difficult to rate those specific morphology features for the interpretation. So that's to say they have limited resolution for the ECG interpretation. And in another research, you can say they use AI ECG for this intervention and also to predict the risk of mortality. And they also highlight important parts with the different features, different colors. You can see here, they have this bright color as important information, but it's difficult to read those specific morphology features. So they also have limited resolution. So that's a research of AI ECG in literature. So our hypothesis in this research is that we assume AI ECG can be used for high accurate CVD diagnosis, and simultaneously it can produce high resolution ECG interpretation. And also because of the high quality ECG interpretation, we assume it can identify new clinical knowledge. So that's three research questions in this research. First, how to develop high accurate, so develop deep learning model to produce high accurate CVD diagnosis, and then how to produce this high resolution for the interpretation, and then how to identify and evaluate effectiveness of those new clinical knowledge. And so with this in mind, we collaborate with our some researcher in Brazil. So this is our collaborator. They collect a large-scale health data set, so use a telehealth network. So this network was used for teleconsulting and telediagnosis, and they deployed in primary care settings. And with the ECG test, they automatically transferred to the cloud server. And so with the 7-year follow-up study, they collect 2.3 million ECG data set from 1.7 million subjects. So this is a plot to show the complex of this data set. They have different types of cardiac arrhythmias and also comorbidities, for example, shock disease, and also the diabetes and also hypertension. And also this data lasts for 7 years. So we have mortality records linked with the national mortality data set. And also we have demographic information. So with this data set, we show the research pipeline. We have electronic records and also the ECG data. We use it for the deep learning development. And then we use this model to perform the interpretable diagnosis and also risk stratification. And then with this result, we use for the identification of new clinical knowledge. So that's a general pipeline. And then we show you the data flow of our research. So we have the raw ECG data set. So this is 2.3 million ECG tests from like standard. So that's from the clinic visit. And then we first exclude the low quality ECG test. So we regard low quality ECG that was those ECG with if they have more than 80% of the data with zero, so they will be low quality and then exclude from data set. And then with this screened clinic ECG test, we perform the first task, the diagnosis and the interpretation of different types of cardiac arrhythmias. So here we understand that there are many different types of arrhythmias. So here in this data set, they include the 6 different types of arrhythmias here. So because they are representing, for example, the first degree AV block, different bundle branch block, different bundle branch blocks, status bradycardia, tachycardia, and also atrial fibrillation. And so this is the first task. And because this is a 7-year follow-up study, and for each individual, they may have different ECG tests. Then for each ECG, for each individual, we matched with only one ECG test. So that will be very first of this ECG test. And then with this matched ECG test, we perform the second task, identification and gender, gender and also for the interpretation, because we observe that we also know that for the we know the gender differences for the development of CVD. And also we perform screening of hypertension because we know hypertension is the largest single contributor to the development of CVD. And finally, we use the result to perform the mortality risk stratification, use our ECG predicted result. So this is the flow and 4 tasks of research. Then I show you the pipeline for our model development. So this is a raw, this is an end-to-end deep learning model. So we have the raw ECG data as a model input, and it can directly get output for diagnosis with our deep learning model. I would emphasize that here we would not have this single denoising and also feature selection, because this is a large enough data set, so that can adapt to different scenarios of the single quality, because we know in real life scenario, the ECG can be very noisy or can be very clean. So here we would not specifically do this signal denoising and other signal preprocessing. So here we use a raw ECG data as model input. So you can see with lead 1 and lead 2 and lead 12 as feature input. Then we learn feature embedding. And then fuse this feature embedding together, we get this feature matrix. And with this matrix, we get output for the diagnosis and also for the prediction. And then with this output, we calculate gradient matrix and use for the feature visualization. So with this highlights these important features here, we can use it for this interpretation and also identify important ECG leads. And this can be used for us to identify digital biomarkers. So this is our model development. And I would also emphasize that because I just mentioned that in literature, it's quite difficult to obtain high resolution for the ECG interpretation. So here we propose a novel isolation and integration module that can allow us to produce high quality for this ECG interpretation. So here I would like to say we have two strategies. First, we treat each ECG lead separately, so independently as a model input. So this allow our model to learn precise features from each ECG lead rather than compilation of those different features from those different ECG lead. So this is the first strategy. And then during the model learning pipeline, we restrict to use a max polling layer, so polling layer. So in that case, the learned feature matrix is just half size of this raw ECG signal. So that can allow us to locate precisely the features with this raw ECG data. So that's our second strategy. So with these two strategies, we can produce a high resolution for the ECG interpretation. So let me show you a result. So first, this is the first task. So using AI ECG for arrhythmia diagnosis. So here we report F1 score because our data is very unbalanced. So normally we observed the prevalence rate will be around 3% for each of those different types of arrhythmias. So for this precession recur curve, so for the right top corner, that indicates the maximum F1 score here. So you can see our model identify those abnormalities with very high accuracy in this holdout testing data set. In particular, our model identify all those atrial fibrillation in this testing data set. And in particular, we compared our model with a junior and senior healthcare professionals. So you can see there are different types of arrhythmias, and this is F1 score from our model. And so there's three junior professionals, the cardiology residents and emergency residents and the fifth year medical students. So you can see for the junior professionals, the highest accuracy would be around 0.876. So it's significantly lower than our deep learning model. And then we compare the model with two senior cardiologists. So you can see our model has similar result to this accuracy to this cardiologist. And then we perform a significant test. So this is a chi-squares test. And so this is our model and compared with junior professionals and two senior cardiologists. And in particular, you can say for this diagnosis of first degree AV block and atrial fibrillation, our model is significantly better than the junior professionals. And for other abnormalities, our model has comparable performance to those from the healthcare professionals. So this is for accuracy for this diagnosis. And also we had external validation on the physical competition. So they have different types of categories. So they include atrial fibrillation, normal condition, and other rhythms here, and also noise data. And so you can see this is the best score for this competition. And so our model is slightly better than those than this computing score. So that's the first hypothesis. We validate this method for the high accurate CVD diagnosis. And then for the second hypothesis is that we would like to say this method can produce high resolution for ECG interpretation. So let me show you the result. So let's say first for the ECG test, this is a detailed lead for, so we show example for atrial fibrillation detection. So we know that atrial fibrillation is a leading cardiac cause of stroke, heart failure, and mortality. Normally, if we say there's absence of P wave in the detailed lead, is most likely is an AF. But generally, there may be some artifacts or fibrillator wave, they can mimic the P wave that can be lead to the misdiagnosis of atrial fibrillation. So now if we look at this ECG test, if we look at the segments A and B, so for example, if we look at A here, the P wave is absent, so this most likely is AF. But then when we look at here, this is a P wave here, this is not AF. So that's really make people confused because for this same ECG test, this is just 10-second duration. And so when we look at different morphology features that can be diagnosed as AF and also not AF, and so we asked the 5 experts to perform diagnosis. Only the emergency residents and the second cardiologists, they successfully made a diagnosis with this ECG test, and the cardiology residents in medical students and also senior cardiologists, they cannot make this ECG test. This highlights the challenge for this ECG interpretation for the diagnosis of different types of arrhythmias. Now, using our AI ECG model, so let me show you results. We calculate importance of each data point in this ECG test, and then with these important features as its bright colors, and then with blue color as less important information. Now let's remove the background color, the less important information. You can say our AI ECG model identify A here with very red color, so that's very important information. Our model identifies this one. And then for the B segment B, this is less important information. That's to say, our model successfully identify A is important, B is less important. And in addition, this model identify this S wave is important and U wave is important. So with a combination of those important features, the model identify this AF with a probability of 0.961. So that's very high accurate compared with 3 out of 5 experts cannot make diagnosis. So this is just one example. And also we show example for the diagnosis of left bundle branch block. So this is excellent knowledge in literature. We know that for diagnosis of left bundle branch block, including this absence of Q waves, noise R waves, and also T wave inversion. And the other result from our model, we identified important features from D2 lead and V6 lead. And now let me show you more details. So this is absence of Q waves in the D2 lead here, and the V6 lead here. And then this is a noise R wave. You can see this part, very slight abnormality here. And also the T wave inversion. We precisely locate this this location of the T wave inversion here. And our model is very robust in identification. For example, for these two duration, they have different time duration for the abnormality here. And our model is very robust in the identification of different time variant features here. So this is interpretation of the diagnosis of left bundle branch block. And also another example is diagnosis of right bundle branch block. So the criteria is M-shaped QRS. So in the V1 lead, so you can see here, very slight, very small M-shaped QRS here. Our model precisely identifies this part. And also we highlighted J wave here in this V6 lead. So this is the interpretation. I show you examples, but then this is just example. How to just for example, how to validate effectiveness of these identified features. We do it in 2 steps. So first, because we say they are important, and then we calculate importance for each ECG lead, for each different types of these cardiac arrhythmias, and then we get the statistics. So for example, this is a distribution for the first degree AV block, of the important ECG leads. And this is the right boundary branch block and the left boundary branch block for the distribution, and the cerebral bradycardia, atrial fibrillation, and the cerebral tachycardia. And so we can say that D2 lead is very important for almost all the different types of cardiac arrhythmias. And AVR is important for 5 out of 6 arrhythmias. And V1 lead is important for 4 out of 6 arrhythmias. Now, if we say they are important ECG leads, then we assume it can be used to obtain high accuracy for this ECG interpretation if we just only use important ECG leads for this diagnosis. Now, let me show you results. We first use identified AVR lead and V1 lead for this diagnosis. Now you can see our model obtained accuracy F1 score is 0.8779. So this is using only the 2 ECG leads. And then we increase the ECG lead to 3 ECG leads with adding the D2 lead here. So you can say slightly increased for the accuracy F1 score. So that further validates the effectiveness of our identified important ECG leads. So this is a first task. Is there any questions so far? Or if we move to the second and third task? Okay, so maybe we can go further. So as I just mentioned, we mentioned that for this AI ECG, they can be used. We think that if we can use for the diagnosis for different types of arrhythmias and also for the interpretation, we also assume that it can be generalized for other different types of tasks. For example, here would be gender identification and also the hypertension screening. Because as I just mentioned that we observed gender differences for the development of CVD, and also for this hypertension is a single large contributor to the development of CVD. So that has significant clinical implications. So let me show you the results. So this is a gender identification using our developed AI ECG model. So this blue curve indicates this performance across all ages. So that has a high accuracy. So you can see here. And then if we say for across different age groups, the young age, middle age, and old age groups, so you can see generally for the young age, they have very high accuracy here. And also for the older age group, they also have accuracy more than 90%. And then we use model to interpret for the gender identification. So that's rare for literature to do this. And also you can see for following for hypertension interpretation. But our model precisely and identify those features in this D2 lead, V1 and the V5 leads. So you can see here, if we remove this less important information, so that's blue color here, and then we obtain this D2 lead, V1 lead, and V5 leads are very important. And then we sum those important information, the weights together. Then we get a weight for each ECG lead for this importance ranking. Now we show some interesting results. So we see the distribution of this importance for each ECG lead for this. So this is for female and this is for male. Now we obtain the importance for this. We identify the V5 and the V3 leads. Leads are very important for both female and male subjects. And then we identify D1 and the V6 leads are very important for male, but less important for female. And then if we think they are very important, and then we do a subgroup analysis. So we use this reduced ECG leads to perform the same the gender identification. Now you can see if we use only the V5 lead, it has an accuracy more than 90%. And then with adding additional V3 lead and also D1 lead, and then our model can identify as accuracy. So you can see gradually increasing. So that's validates this effectiveness of those identified dominant ECG leads. So this is for gender identification. And then we have this subgroup analysis. And you can see we perform gender identification across a young age, middle age, and older age groups. And generally, we can say the young age has the highest AUC score across those different population groups. And then if we compare these different ECG leads, for example, only a single ECG lead and different combinations of these two and also three ECG leads, and then we identify that the V5 is dominant, and the V5 plus V3, so the two ECG leads has the highest accuracy across two combination of two ECG leads. And also, if we identify for this three ECDs combination, we identify adding the D1, V3, and V5, it has a higher accuracy than other combinations. So this is a subgroup analysis, and this actually can maybe used for this for us to develop deep learning model with a reduced ECGs, for example, one or two or three ECGs, because this can reduce save our computing power or other deployment in other applications in the scenario if we cannot obtain the 12 ECDs. And so this is second task. And for the first task, so for the third task is a hypertension screening using our AIC model. So first we report AUC score here. The accuracy is 0.839. So that's using the 12 ECD test. And then, as I mentioned, then we use a similar method to perform the hypertension interpretation. So we identify the D2 lead and the V5 lead is very important. And then we identify those important features. With these features, we obtain the distribution of this important. So it's very interesting to say, normally more than 80% of the subjects, they have the V1 lead is very important for hypertension screening. And also for the D2 lead is also very important. Then if we only use a V1 lead for this hypertension screening, it has a similar accuracy to that use a 12 ECD test. And then if we add D2 lead, it's slightly increased a bit for the accuracy. So that's that'll be quite useful because nowadays people are using wearables for this hypertension detection. Now, if we can use only V1 lead, that can guide us to how to develop this kind of wearable device for this hypertension screening. So that's would be some insights for this result. Then we show you the age comparison for the hypertension screening. So you can see this is across a young age group using the all 12 ECG test and also single ECG V1 leads, and also the middle age group and also the age groups. And generally, we can see the older age population has the highest discriminant identification score across all the population groups. And also, I show you the result for the population for the gender comparison. So here you can see for the female population, generally has a high discriminative identification score across this comparison. So this is a third task for hypertension screening. And finally, I show you the result for the mortality risk stratification. So that's different plots explore data distribution. And this figure I just showed you. So this is shows an intercollection of different variables. And so this is mapping of different currents. For example, here would be different types of arrhythmias, and then for female and male, and then the flow goes to hypertension, and finally linked with the mortality. And then we explored the feature importance. So we identify the hypertension, status tachycardia, atrial fibrillation, and also age would be very important. And then for the hypertension, we identify the female groups generally has a higher ratio than the male group here. And in the middle age, so we say the male group actually have higher mortality rates than this female group. So this is distribution. And then we show you the survival analysis. So here, we identify this different survival rate for different public cohorts. So here, for example, this plot shows a hypertension with different types of arrhythmias. So for example, this first degree block, atrial fibrillation, status bradycardia, and also different types of bundle branch blocks. And in each subfigure, so each curve indicates different population condition. For example, for the red curve, that means the population, for example, have the hypertension and also first degree block. But for the purple curve here, the population only have the first degree AV block, but they do not have the hypertension. Now, if you compare these two curves, you can say they have significant differences for these two population. And if this population have hypertension and also first degree AV block, then they will have a high risk of mortality. But then if you look at this curve, you can say whether the population have hypertension, if they have left bundle branch block, they will have a high risk of mortality. So this result, this also you can say applied for the atrial fibrillation. Whether they have hypertension, if they have atrial fibrillation, they will have a high risk of mortality. So this model, in this sense, it can be used for this personalized risk prediction. And then I show you more result for the hazard ratio for the comparison. So this is use original data set, use a traditional way to calculate hazard ratio. And so this is our using the our ECG predictive variables to calculate hazard ratio. And when we compare these two tables, you can say they have very similar, actually have very similar hazard ratio in terms of hypertension, different age groups, and also different cardiac arrhythmias. So this shows that our ECG predictive variables demonstrate comparable risk simplification with regard to those derived from the traditional risk score. So this is my talk today. Thank you.